Hello everyone, welcome to From Concept to Circuit new video. In this video, we make a very useful tool with ADALM Pluto. This tool is a frequency response analyzer up to 3 GHz. First, we configure our ADALM Pluto TX as a signal generator to generate a sine wave. Then we apply that sine wave to our circuit, and then we connect the output of that circuit to our receiver and measure the amplitude difference using the lock-in amplifier techniques we described in the previous videos. This is a very useful tool to have in the lab because it gives us the ability to analyze any circuit frequency response with very good accuracy and high frequencies. So let's get started. Okay, now we want to see how we can uh, in the simulation or calculation how we measure the frequency response. So we apply a sine wave at the input of our circuit that we are interested in. In this case, this is a low pass filter, a very simple low pass filter made from an RNC circuit, right? We apply a 1 volt peak to peak sine wave at the input and then measure the measure the output uh, response. This is a transient simulation, right? So you can see the amplitude has been degraded, which if I measure it here, which I'm measuring here, it's around point, zero point 0.7, around approximately zero point 0.7 volt when I applying a 1 volt at the input, right? Which is showing that actually we are at the 3 dB frequency of this low pass filter. But you also can see, because your input has a phase of 0, you can see that in terms of phase, you have a phase displacement between the output sine tone and your input, right? So when you do that for a given frequency, you just need to repeat this for uh, for many frequencies that you are interested in. Uh, and put the results besides each other, which is this AC simulation. The frequency response is starting from 0, uh, and when it reaches the omega 3 dB or 3 dB frequency of this circuit, which is around 318 megahertz, you can see that there is a 3 dB degradation in the amplitude response, and also the phase difference becomes 45 degree, right? So this is how uh, the frequency response of a circuit is measured, right? So we just need to do the same. We need to apply a sine wave at the input of our circuit. Using our ADALM Pluto, we just can use the transmitter, create a sine wave, apply to the circuit, and then measure the output uh, uh, for that exact frequency, measure the amplitude and phase. Okay, now let's go to the code, see how we can implement this using our ADALM Pluto. The reason I put this block diagram side by side of our code which is that when we do our analysis, we can just easily refer to this block diagram and see what is happening exactly behind the scenes. This is why I really like this block diagram. So, okay, first we need to, using our TX, we need to create a sine wave that we want to give to our circuit that we want to measure its frequency response. Uh, what we do, because we have already an INQ generator here, right? We can just set the TXLO to that frequency that we want, and it should on paper create that sine tone. But the issue here is that, as you can see here, for noise reduction in our SDR, we have 200 kilohertz to 56 megahertz uh, filter here after our DAC, right? Which is which is basically uh, wants to create, basically wants to reduce the tones at the output of our DAC, right? So if we just uh, make a constant voltage at our uh, output of our DAC, the chances are that our filter may reject it, right? So what we do here, we just for a better for lower attenuations, we create a sine tone also at our output of the DAC, which is a very low frequency sine tone, uh, which as you can see, I generated here. I defined the TX frequency here to be around 250 kilohertz, and then uh, this sine tone comes here, it will be up converted by a mixer, then going to our output, right? So it's just that there is a little bit of shift at the output of our SDR because I'm generating this extra sine tone at the output of DAC, which in my receiver, I need to reverse it. I need to uh, um, uh, uh, divide the received down converted signal by that same um, sine tone, so I don't see the effect of that sine tone, right? I'll show you how we do the sweep, but as always, we need to initialize our SDR, which is just first connecting to it, AD9361. This is the IP address. Then we define the sample rate, which we give it here. Uh, in this case, I just here for just first initialization, I define a center frequency, which is here just an arbitrary number. But in my sweep, actually, I sweep this frequency. I'll show later. Uh, I just define some other variables here, number of samples, which is how many samples we read or send in our TX or RX buffer. Then some other things like sweep start, which is like what is the start frequency in which we start our sweeping. A stop, how many steps, what is the delay between them, how many buffer clear we do each time we change the frequency and we want to read back the new RX data, and how many RX read we do each time, right? These are just like some variables that we see later in the code. Then based on this, I define the sample rate, RX and LO, which here is, this is just for initialization. We in the actual sweeping, we sweep these things. RF TX bandwidth, which I set to exact sample rate. Enable channels, because I'm just using the first channel for TX, I'm just setting this to channel 0. As I mentioned in the previous videos, for this scenario, we don't want the SDR VGA variable gain amplifier doing any processing in my received power, because we just want to measure the raw received power, right? So that is why we set this to manual. And also here, TX cyclic buffer, we make it true, meaning that uh, each time the TX is done sending the sample that we defined here, it just starts over and starts sending the same thing again and again. These are just the hardware gains. I defined the TX um, uh, gain to be minus 30 dB so that we output a very low power at the output of our TX. Although we have another 30 dB attenuator in the line, so we don't put a very large power at our input of our RX, but I just set it to 30, and as I mentioned, because now here is minus 30 and we have also a 30 dB attenuator, I set this to 60 to cancel the overall attenuation we have in the channel. I talked about how we create the sign the TX data in previous videos. Uh, Basically, we define for this case, because we just want to create a sine wave, a complex sine wave. We just say e by power of 2j pi. and our Tx and T, which is generated basically based on our sample rate. The step size is 1 over sample rate, so number of steps over the sample rate will give us a vector for our time. Then we generate the Tx signal, we scale it to full DAC, full scale, and then send it here, right? Then in our RX amplifier, in our RX lock-in amplifier, I mentioned this in the previous video. We have this extract amplitude and phase uh, function that basically what it does is that the RX signal, what it does is that first for the received RX signal after down conversion, which is coming here, we first multiply it by reverse of this sine tone that we generated in our TX, that 250 kilohertz. So now we have just a DC tone. Then, uh, 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 as I mentioned in the previous video, we need to create a low pass filter. In this case, I try to, compared to the previous video, I try to make the low pass filter more strong, meaning that it has more attenuation and it's using a Kaiser filter uh, with a very low cutoff frequency and very low transition width. This I used FIR win function and also Kaiser or the from some Python libraries to generate the order of filter, the number of tabs that filter needs, and the beta of that uh, uh, Kaiser filter. Then once we generate these coefficients for our low pass filter, we just pass it to this low pass filter function, which applies a low pass filter to our signal, right? Then we measure the amplitude, which is the absolute value or magnitude, and the phase, which is the angle. The issue here is that I'm in my previous video, I showed this will give us the amplitude and phase, right? And it worked very good, but we have some uncertainty using this lock-in amplifier we created with our ADALM Pluto when we are measuring the phase. Why? Because um, one source of uncertainty comes when because um, let's assume that we send a signal, then by SDR.RX, we read the data, we read the ADC data, which means that the time that we read the ADC data is just some arbitrary time that is based on when in our Python we read back the ADC output. What happens in this scenario is that the exact timing of when we read back the ADC data may not be aligned to exact time that this sine tone with phase, which is here generated with phase 0, is received here. There we have a sine tone here, and it's just fluctuating between +1 and -1. And because we don't have the exact definition of when we start reading back this sine tone, we can read uh, starting from any point in this sine wave, right? So then what happens here, you can, when you are reading from, starting from any point in this sine wave, you are starting from an arbitrary phase in this sine wave, right? And this issue comes into picture when we are measuring the phase. So we need a mechanism to lock the phase, meaning that we 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 kind of uh, uh, by using some synchronization, we know exactly when to read the ADC data or when the sequence starts, and we start reading from that exact time, which will we cover in our next videos when we want to go to some advanced modulations like cam modulation, which we need the phase information in. So in those future projects, we need to see what are the ways to align the phase read in the receiver, um, so we can measure the phase with much more certainty. Uh, there are many ways. For instance, we can have a synchronization frame sent with the actual data, which will help us to sync the transmitter and receiver. We'll go back to this problem in the future projects and in the future video. So we just, for this one, we are just measuring the amplitude, right? Um, Coming further down to the actual, now we want to start the sweeping. We create a vector for the frequency from the sweep start, and the sweep steps. So this is the vector for our frequency. These are the functions I use for plotting, but the main thing happens here when we are performing sweep. What we do is that we we start sweeping the frequency for inside these frequencies vector. Uh, we have an index that uh, getting incremented as we go to in this loop. For current index, we fetch the frequency and then lock this TXLO and RXLO to that exact frequency, meaning that we just now we are looking at the same tone at our input and our output. Then we clear the buffer. We wait some time so we don't read the previous data. Then we read the new data with the number of reads that we defined on top of the um, code that I showed you. Then once we have the RX signal, we just pass it to that extract amplitude and phase function and extract the amplitude. This way, we just create a vector for the amplitudes for the frequencies, and this is how we create our um, frequency response measurements. Now let's go to the example that we were looking at the beginning of the video. So this is the low pass filter that we wanted to that we were measuring its frequency response at the beginning of the video. VLFG 1525 plus, DC to 1525 megahertz. If I come down in the data sheet, you can see the frequency response of this circuit, right? It has a sharp drop which is around F3, which is the rejection band. Uh, Assume that it's around 2.1 gigahertz. Then it comes back up again around F4, which is 2.3. Then it goes down again, right? But it has a very flat response, you can say, up to F1, which is 1525, right? So we have this, and now we created this frequency response measurement circuit that exactly give us the tool to measure the frequency response of the circuits that we want easily with ADALM Pluto. Let's see now how our code, when we run it, how it matches this datasheet. Okay, now I have started the code for our locking amplifier. Keep in mind that we may have, because of the reference that we have used in our ADAM Pluto is not a very robust clock reference, so there might be hundreds megahertz frequency shift compared to this datasheet, but we actually see very good behavior from our locking amplifier. If I just pause here for a moment, you can see that we see the very similar shape. The amplitude, we can calibrate it better because we definitely have the cable, also the attenuator in the line, um, plus the PCB losses. But you can see the bend here happening around 1.75. If I want to see what is the F2 here, it's around 1.76 gigahertz, which is very close to what I'm seeing here. Also, you can see it comes down from 0 to, if I see here, I see around 65 uh, here attenuation, which is exactly what I'm seeing here. Then it goes back up again at F4. F4, here we are measuring 2.16. If I want to see what is the F4 here, it's around 2.3. So here at high frequencies, um, we are a little off in terms of measuring the frequency, which we can definitely improve by improving our reference generator. Also, this circuit, these numbers for the frequencies are typical, so we might have some frequency shift from the actual fabrication of the circuit. So I resumed the sweeping here. These are just like some basic functions built in here. You can see it comes back, comes down, goes back and comes down again. We see the same behavior here happening as we continue and we go. Here, one thing to note here that we are seeing some uh, rippling here. And one of the reasons is that our attenuator is also supporting up to 3 gigahertz, and we are getting close to that one. But for this case, because I don't want to fit the cable exactly to our ADALM Pluto without the attenuator, I just kept this as is. But hopefully in the future we get a better attenuator. That's it. You have it. Please, uh, please give me feedback. Please comment and share this video so other people can see. I think now that we have built a foundation of how to detect the amplitude, how to lock in terms of frequency, how to lock the TX and RX, we can move on to other materials such as some RF communications, some wireless communications, modulations, and see how we apply these theories to lock the frequency, lock the amplitude, lock the phase, and transfer data um, wirelessly. Hope you enjoyed it. Thank you.